Hey everybody, it's Ripley back again. I told you we were going to take derivatives of log functions, which is awesome. It's so easy. This is the coolest part. It's very simple. All that we're going to do is, if I have y is equal to the natural log of x. Once we have the natural log of x, we can do the other ones at will. It's very cool. Nothing to it. And I want to know what y prime is. That's all I want. That's my goal, is to figure out what this is. And then I'm actually going to show you kind of something cool that you can do with logarithmic differentiation, which is kind of fun and it's helpful. Okay, so here we go. Again, I'm stuck, right? I mean, I know all my trigs. I know all my inverse trigs. I know my wait a sec. I know my exponentials. I know the derivative of a to the x. So let's think about this. If I take e to the both sides, do you agree that I get e to the y is equal to x, right? Because if I go e to the, and e to the natural log of x is x. True? So these are algebraically equivalent. So let's take the derivative using implicit differentiation, which is this amazing tool. If I take the derivative, do you agree that I get e to the y, the derivative of e to the blah is e to the blah, times d blah. So there's this little understood 1, dy over dx, and this is equal to 1. So dy over dx is equal to 1 over e to the y. Hey, guess what e to the y was? Again, natural log of x is a function of x. We know what it looks like. It looks like this guy, right? Now, we know that x can only be, this can get a little bit crazy, so we got to be careful. So if this is 1 over e to the y, then this guy turns into 1 over x, right? Now, we got to be careful. Let's make sure we understand something. All right, I'm going to put this guy in red so we can see it. 1 over x looks like this, really badly drawn. Let's do that a little better. 1 over x looks like that. However, the natural log of x only exists for numbers greater than 0, right? That's its domain. The domain is the open interval from 0 to infinity. But 1 over x spits out values over here, right? So we got to be really, really careful. We know that 1 over x exists for all real numbers except x equals 0. So you might get confused in terms of what you're doing with this. So you just go, okay, whoa, let's slow down. I know the behavior of the natural log of x. I know what its mother graph looks like. It passes through 1, 0, and it's kind of goofy. It doesn't have this. There's a vertical asymptote at x equals 0. No horizontal asymptote. This thing heads for infinity. It gets there super slowly, but it gets there nonetheless, okay? All right, however, just remember that the derivative of the natural log of x is only going to work. The derivative is only going to be continuous in values where the original function itself exists, where it's continuous. So this would be true for values of x that are greater than 0. And that's how it works. Now, here's the cool part. Now we have this cornerstone upon which we can build. What if I want to take the derivative, let's see, y equals log base 17 of x. Well, I know from the logarithmic lecture that I watched earlier that I can rewrite this as the natural log of x over the natural log of 17. I just changed base. I don't know any other derivatives per se except the natural log of x, right? So remember, natural log of 17, all that is just a real number. So y prime is going to equal 1 over x times the natural log of 17. And I'm done. So I can write a general rule. If you like general rules, there's nothing wrong with that. If you like a nice general rule, then y is equal to log base a of x, I know can be written as the natural log of x over the natural log of a, which implies that y prime, f prime of x, dy over dx, whatever you want to call it, is equal to 1 over x times the natural log of a. All right? Okay, cool, easy. That's it. Like, we're done as far as taking derivatives of logarithms. That's it. We should probably give a little nod to chain rules. So let's say that I had f of x is equal to log base 2 of 5x squared minus 9x plus 1. All right? And I want to find f prime of x. Now, I can use my little rule right here, or I can actually take a step here and go the natural log of 5x squared minus 9x plus 1. And remember, this guy's only going to work for positive values when this whole chunk right here is greater than 0. That's only going to work if that's greater than 0, right? Because natural log, you plug in a negative number and in a natural log, it's not going to know what you're talking about. All right, and then on the denominator, I get this natural log of 2. So the derivative of the natural log of blah is 1 over blah. So this is going to be 5x squared minus 9x plus 1. I'll put that in parentheses because I get this natural log of 2 constant along for the ride, times d blah. Well, what's the derivative of the blah? Well, it's going to be 10x minus 9, right? And that's it. If I wanted to rewrite it, I could, but I'm not going to insult your intelligence with that. You can do that. Derivative of the natural log of blah is 1 over blah d blah, and we're done. Okay? Now, I'm going to show you where logarithmic differentiation can be really, really helpful. Watch this. Let's say that f of x was equal to x minus 2 to the 5th times 3x plus 1 to the 4th over x, let's go x squared minus 1, let's go x squared plus 1, so we don't want to factor that, squared times x cubed minus 5 to the 8th. And I want to find f primed of x. F primed of x, right? I want to take that thing's derivative, all right? So I really got to think about this for a sec. This could be awful, right? Because look at everything that I would have to do. I have to take all kinds of derivatives. I got to take products. I got to take quotients. I have to do chain rules. This is going to be awful. However, watch this. This is the coolest part. What I'm going to do is I'm going to let y equal this. And then I'm going to take the natural log of both sides. I can do whatever I want as long as I do it to both sides, and I've changed nothing. So the natural log of y is equal to the natural log of, and I'm going to just cheat and be lazy here for a sec. I'm just going to stuff this guy into here. Okay? Now, I know that the natural log of y is equal to, well, the natural log of all of this. Now let's think about what this really looks like. The natural log of a product is the sum of the natural logs. So I'll write that out first. This is going to become the natural log of x minus 2 to the 5th plus the natural log of 3x plus 1 to the 4th, right? And then I'm dividing by these, so I will just subtract the natural log of x squared plus 1 squared minus, respect I negative. You're going to say, but Ripley, that's a product and we're adding. Yeah, but we're dividing by this entire term. So this is minus the natural log of x cubed minus 5 to the 8th. You see what I did there? Now, let's look close. Let's make sure we understand what happened there. I used the laws of logarithms to split this thing up. So now instead of having all these products and quotients, I have sums and differences. We love sums and differences because the derivative of sum of the derivative. Derivative of the difference in derivatives. But wait, there's more. It's like the Ginsu knives. I also know that in this case, the natural log of y is equal to, now you ready? I can remember the rule about exponents? They become coefficients. So I can rewrite this as 5 ln x minus 2 plus 4 ln 3x plus 1 minus 2 ln of x squared plus 1 minus 8 ln of x cubed minus 5. Isn't that pretty? Gorgeous, right? Look how pretty that is. All right, now here we go. This is the big drum roll. This is where it gets a little bit crazy. All right, I'm going to take the derivative with respect to x. Okay, the derivative of the natural log of blah is 1 over blah d blah, right? There's that dy over dx again. There's a little understood one there, and that's the thing that I'm trying to solve for, right? Because this is f of x or y. So if I'm looking for this thing's derivative, and I'm looking for dy over dx. And this is equal to, now watch how easy this is. That all of these coefficients are just along for the ride. So this becomes 5 over x minus 2, right? Because the natural log of x minus 2 is, the derivative of that, is 1 over x minus 2 times the derivative of x minus 2, which is a little understood 1, plus 4 over 3x plus 1 times the derivative of 3x plus 1, which is 3, right? I'm just using chain rule, minus 2 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, minus 8 over x cubed minus 5 times the derivative of x cubed minus 5, which is 3x squared. Now, I'm going to do two things at once, because if you look at this, watch, I'm going to change colors so you can really see what's going on here. Notice there's a y right here. I don't want a 1 over y dy over dx. I want a dy over dx all by itself. So I'm going to do two things simultaneously here. I'm going to multiply both sides through by y. Those y's cancel, and I end up with a y here. And then you may go, Ripley, what is going on with this y? What is this y? Oh, it's my original function, and there it sits all nice and pretty. So when everything is said and done, and I'm going to write this up, and then you might want to sit with this a little bit. dy over dx is equal to, you ready? 5 over x minus 2 plus 12 over 3x plus 1 minus 4x over x squared plus 1 minus, what is that, 24x squared over x cubed minus 5. That's a cube, by the way. This whole thing is in parentheses, and it's times y. Well, I don't want a function of x and y's, especially since I started with a function of x. So this whole thing is times x minus 2 to the 5th times 3x plus 1 to the 4th over x squared plus 1 squared times x cubed minus 5 to the 8th. This y and this y are the same, and we're done. It's not the prettiest derivative in the entire world. I hope you don't think that it is or that it will be. However, it works really, really well. Now there's one other function that I want to show you how to do this, okay? And we got to use logarithmic differentiation. It's a type of function, all right? And I'm going to give you the general form. Okay, just because I want you to see how this works. So let's say that I said I want to take the derivative of sine of x to the x. Now, I'm not going to lie to you. Ugh, what is going on here? Sine of x to the x, okay? That is an ugly function. That's a crazy function, right? I mean, because this guy is either going to be, it's going to give powers, or it's going to give square roots, cube roots, nth roots, depending on the value of x. Like, it's hard to even visualize what this thing would look like. But what I'm going to do is I'm going to take the derivative of f of x in general form raised to the g of x. So I have a function raised to a function. Like in this case, I had sine x raised to the x. I could just have easily done sine x raised to the x squared. And I want you to see what I'm going to do here, because this is really helpful. And then this will be the last thing that we talk about in this section. Well, there's one other quick little thing. I'm just going to define e for you, just because while we're in natural logs, we might as well talk a little bit about e. All right, so I'm going to use the same trick as before. I'm going to take the natural log of y is equal to the natural log of f of x raised to the g of x. I'm going to use the exponent rule of logarithms. So I'm going to write this as the natural log of y is equal to g of x times the natural log of f of x. Remember, exponents become coefficients. Now I'm going to take the derivative with respect to x. I'm going to use implicit differentiation. Super powerful tool. I get 1 over y dy over dx, right? We've seen that a bunch. Now this is a product, so I got to be careful. This is going to be g primed of x times the natural log of f of x plus g of x as it stands times, now we got to be careful here, we got a little chain rule, 1 over f of x times f primed of x. Okay? That's pretty cool. That's pretty easy. Now look what happens. If I multiply through by y, then I get rid of that y here, and all that's left on this side of the equation is dy over dx. So I can rewrite this as dy over dx is equal to g primed of x, natural log of f of x, plus g of x times f primed of x, all over f of x. Now this whole thing is times y. Well, what was y? It was the original function, f of x raised to the g of x. Whoops, raised to the g of x. So look. If I want to try and do this, look at what happens. I can either use this as a template, but that's really complicated. I just do this by hand again. I would do the natural log of y. I'm going to skip steps, so we're going to come down here. Natural log of y is equal to x ln of sine of x. You see what I did? I just skipped a step. All right, I know that if I differentiate the whole thing with respect to x, I get 1 over y dy over dx is equal to product rule. So derivative of the first is 1 times the natural, I should probably put that in parentheses, shouldn't I? Natural log of the sine of x, derivative of the first is 1 times the second as it stands, plus the first as it stands, times the derivative of the second, which is 1 over sine of x, times natural log of blah is 1 over blah d blah, so this is going to be cosine of x, right? Then I multiply through by my y, and I clean up as I go. So I know that dy over dx, after I multiplied through by y, is equal to the natural log of sine of x, plus, now I can even get tricky here. I know that cosine of x over sine of x is cotangent of x. So I can write this as x cotangent of x, right? All I did is algebraically manipulate this. Now I can either write this as a times this y, but I remember what y started out being. Y started out as sine x to the x. So this is sine of x to the x, and I'm done. Don't forget these parentheses. If you forget the parentheses, you are going to get popped. Whew, that's crazy, isn't it? All right, implicit differentiation is super useful, and we're going to use it a bunch. It's certainly not going away. Before we're done, though, let's talk, I want to talk about where E comes from, just because I'm feeling a little bit crazy. And this may show up in many texts at this point, at this topic. You end up with a definition of E. And remember, E is Euler's number, right? And it can be written a lot of ways. We already saw E as the number defined in a limit. You remember that crazy one when we were actually showing that the derivative of e to the x was e to the x? Excuse me. But the best way the most common way of defining E is the limit as x goes to infinity of 1 plus 1 over x raised to the x. That's one way. Or you can also write this as the limit as x goes to 0 of 1 plus x to the 1 over x. Those are identical ways to define E. If you don't believe me, put them in your calculator. We know that E is approximately, believe it or not, I like E better than pi. It shows up everywhere, whereas pi just shows up in circles, which are not the most natural of all creations, if you know what I'm saying. E is approximately 2.71828, blah, 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 right? If you don't believe me, put just a big number in for x, 100,000. If you do 1 plus 1/100,000th, the whole thing raised to the 100,000, guess what? You're going to get really close to the value of E. Right? Likewise, if you don't believe me, put a number really, really close to 0, like 0.0000001. So you would take 1 plus 0.000001, however many zeros I said in the first one, just paste, right? Raised to the 1 over 0.000001. Bam! And you're going to get a number really close to E. All right. That's enough, Dr. Ripley. Quit your yammering. I will see you in the next section. Where we're going to talk about, I don't know, well, it's not the next section, depending on which textbook you're in or what you're looking at. But the next section that I'm going to talk about is forthcoming here in just a sec. So hope you enjoyed it. Hope it was helpful. And believe it or not, we're pretty much done taking derivatives. We have all of the skills now. We got trigs, inverse trigs, we have logarithmics, we have x to the n's, we have a to the x's. We got it all. We got these crazy functions right here. What the heck? Never even heard of those before, and now I can take its derivatives. The reason we can do that is because implicit differentiation is such a powerful tool. All right, I will shut up and let you guys sit back and enjoy. Have a wonderful day.